Welcome, everybody. My name is Randy, and welcome to the November speaker night for the Mississauga Center of the RASC. I haven't done this for a while, so I have to remember how to do this. We're very, very fortunate here in Mississauga. We have a great source of excellent speakers from universities and colleges around the area. And we often have guests from York University. And our speaker tonight is here. I think he spoke at least once
I
before.
think one time.
One before. Yeah, probably
Years and years and years.
quasars or
Oh.
something like that. Anyway, our speaker's Jesse Rogerson from York University. His bio is online, but if you listen to the radio or TV, you hear Jesse quite often because his expertise is called upon to talk about comets from alien planets and all these other weird things that are happening in the sky these days. And so that's a lot of fun. But also, Jesse is an educator. He does have a PhD, and he knows all about quasars. If you want to talk about quasars during the break, he's the guy to talk to. But he's an educator, and he enjoys, like many of us, just spreading the word about astronomy and science to students at York who are not in sort of science streams, first year, second year students, that kind of thing. So he's a great educator, a great communicator, and he and another astronomer at York, John Moores, who's more into planetary science.
He was here. He was here, right?
He was here.
He was here.
He was standing right there. And they both collaborated on a book that Jesse's going to talk to you tonight. So with that, I'd like to introduce Jesse Rogerson, and he's going to tell us all about his work on a book, Daydreaming in the Solar System, which is a great read. He actually had some copies that he'd love to sell you. But I'm sure you're going to enjoy this very much. Please welcome Jesse Rogers.
Sorry, I have one here. So thank you, Randy. That was great. I like being introduced. I must admit I'm a little nervous. I haven't actually presented in front of a class for a while because the teaching I'm currently doing is online. So I'm like, oh, right, this is what it feels like. And I love it. Absolutely love it. So it's good to be in front of you all. I know that you had John here at some point, I guess about a year ago, roughly. So hopefully I can get like a different angle of this book. I think, I can't remember when he came, but I remember he said he had a good time when he was here. So what I'm going to do is give you a little snapshot of our book, but it's not about the book necessarily. It's about what you're reading here on the screen, or if hopefully you maybe taken a skim over this. I know there's a lot of words there. The idea that no humans have really gone to the places in our solar system. We've been to one, right? We've been to the moon, and that's fantastic. And we've done, and when we learn about the moon, when you learn about the moon or read about it, inevitably you'll end up at the stories that those astronauts have told. You'll end up at, probably everyone in this room, or at least a few people in this room have heard the story about what the astronauts thought the moon smelled like, right? Has anybody heard that before? No? Yeah. What does it smell like? Gunpowder. Gunpowder, right? I mean, you would never. So the astronauts, they land on the moon and they're so excited. They get out and they start walking around, and the lunar regolith is all sharp because it doesn't erode the same way rocks do here. There's no wind or rain, so it's all sharp, jaggedy rocks that clings to their spacesuits, and then they come inside the from outside, and they're like, oh, what's that smell? And they're like, it smells like gunpowder, and apparently that's what the lunar regolith smells like. That idea of being able to like actually know what a human has sensed while in those places is not something we have for anywhere else in the solar system. So what you have here is a quote from our book. No human's ever been watching clouds on Mars, or been parachuting beneath the Titanian clouds, going below the cloud deck on Titan, sailing on the Titan seas. No humans has ever done any of this. So we wanted to think about that. What would it be like for a human to actually do that? Now, I'm going to sort of reintroduce myself. Randy, you did a great job, but I think this is relevant a little bit. This is me. My hair seems darker, and it was only like 5 years ago. When so I did a PhD at York. I did a master's at York. I was at McMaster before that. If anybody's never been to the Alan I. Carswell Observatory, you can go check that out. While I was doing all of my grad work, I found quite a fun passion teaching people, as Randy said. I really like just engaging with people about science in general, really, but obviously astronomy is my true passion. So I got a bunch of different jobs. I worked at the Ontario Science Centre for a long time. One of the saddest things that has happened to the city since the McLaughlin closure is the closure of the Ontario Science Centre. Don't get me wrong, the Ontario Science Centre staff are amazing. They're keeping the dream alive. They're doing great stuff all over the city, and they're going to eventually get a building again. But the closure of the building that we had is super, super sad. I used to work there. I had a great time engaging with people there. After my grad school, I went to Telespark in Calgary, and I worked there as an educator for a little while. I ended up back in Ottawa at the Aviation and Space Museum as a science advisor there. There's me standing in front of one of the Canadarms that went up. Very young, thin, and dark-haired. And here's this is a much more recent picture, gray-haired, and back at York, teaching science to non-science majors and just generally engaging with astronomy with people. And I would say that I'm a product of the Science Center industry, or more that the reason I worked in the Science Center industry is because I aligned a lot with what they were trying to do. And here's some mission statements from those. You don't got to read them, but the Ontario Science Center says things like adventure, curiosity, creativity. Telespark, same thing. Play, create, arts, science. And these are really good avenues to engage science and astronomy and space and anything really that you're trying to teach people about or learn with each other. So I ended up there. I ended up in this industry doing these things because of the way that industry acts. And then I found a really great outlet at York in a department called the Division of Natural Science that Robin also is a part of, that does very, very similar things, where you're engaging people through science, through art, through creativity. So anyway, the reason this is all relevant is because this is where the idea was born. John and I, well, at first it was just me. I was looking at this moon. This is the moon. Does anybody know this moon? Many of you. Yes, it is no, sorry. It's not a Jovian moon. No, it's not. That you're talking about Ceres. No, this is a moon of Saturn. Enceladus. Yeah, Enceladus. Says it right there. Enceladus is an ice moon of Saturn, right? So what you're looking at is a moon entirely covered in water ice, H2O. That's what you're looking at. It's like a big skating rink, right? It's cracks and fissures and stuff from the ice being folded and moved, betraying the existence of some kind of geophysical, some kind of activity happening below the surface. Much the same way our continents move and buckle, as does the ice of this surface. When we sent a spacecraft here in the early 2000s called Cassini, it arrived at this moon and saw some incredible things. Some plumes, jets. These are geysers. What you're looking at is active water, H2O, shooting out of the surface of this moon at an incredible large amount. This is an actual image taken by Cassini of this like ejecting from the surface of this moon. So much so that there's it might be tough to see, but the moon is right there. Oh yeah, this is okay. There's the moon Enceladus right there. And behind it and in front of it is this trail, which is actually, as the moon circles around Saturn over and over and over again, it leaves behind a trail of ice crystals, H2O ice crystals, effectively creating a ring around Saturn continuously. We call it the E-ring. Now, what's happening, this is over a few years of work, after looking at all of this data that came back, scientists have figured out that we have this surface this ice crust, tens of kilometers thick, maybe even 100 kilometers thick. It's hard to say. It's probably different in different places. And below that is a massive global ocean of water, H2O. There's a ton of water at this moon, and more than likely, part of the reason why it's got jets shooting stuff up is that there's activity below. There's probably, given the conditions in the orbit around Saturn, the way tidal heating works and a few other things, this is probably a moon with a warm center. It probably has hydrothermal vents at the very bottom of that ocean. And there's what you're seeing is outgassing, or I guess out spraying of H2O. It's an active moon. It's got a ton of water. It's a really interesting place. So I'm not here to talk about the science of that moon. I'm here to talk about what fun you can have with your brain when you daydream about these weird places and how it can help you explore these places. So I was sitting, this is an astronaut version of me. And I was sitting in my office one day. I'm like, I wonder what would happen if I jumped into those plumes. That was literally what I was thinking about. Not about like what the chemicals were, which is salty, by the way, or not about whether there's life there, which would be really interesting. But I want to know, if I was there at this moon and I jumped into that plume, what would happen? That was my thinking. So in particular, I was interested to know, if I jumped in, would I be launched up off of the moon and join the E-ring of Saturn? Or would I fall to my demise into the crevices of this ice world, never to be seen again? Or maybe I'd meet some life down there. I don't know. So let's figure it out. What do we need to know? What do we need to know to answer this question where little astronaut Jesse is going to either fly into space or fall to his death? Gravity. Yes, we need the force of gravity. Okay, hold on. Force of gravity. Oh, wait. Oh, there we go. Force of gravity. What else do we need? So we're already, yeah, you're nailing it. We need to know force down, and we need to know force up. That's pretty simple, yeah? Escape velocity of the moon. Ah, interesting. Yes, that's a good one. I'm going to write that down. Where's my pen is not working. The escape. Anything else?
Surface area of you.
Surface area of me, totally. Surface area. Yeah. I'm going to put that under here. There's one up there. Yeah. My mass, modest. Okay. You're nailing it, right? This is exactly the thoughts that were going through my head. There's actually some simple equations for this. The first one, the force of gravity, is easy. G, M, and, bear with me. G, M over R squared. Gravitational constant G, the two masses, the mass of me, the mass of the moon, and then R squared is my distance. R is my distance from the center of the moon. That just gives you the force of gravity. That's Newtonian physics. Pretty easy to get these numbers. The force of the wind is one I had to look up. I didn't know that one. So, but that equation is one half density of wind, velocity of wind squared, and surface area of me. Nailed it. And if those two, what would happen if force of gravity is great? Oops. Sorry. What would happen if force of gravity is greater than force of wind? Down, right? What would happen in the opposite? Right? Pretty simple, right? You just you get some simple equations, do some math, we can figure this out. I had no idea where to find that information. I was lost. Density of wind, did Cassini measure that? I don't know. How fast the wind is moving, did Cassini measure that? I don't know. So I said, hey, John. This is where John came in. I emailed John. I'm like, John, listen, I'm trying to answer this really weird question. Bear with me. I really want to know the answer. Can you help me? And he said, oh yeah, totally. I know where to find all that information because John is an incredibly good planetary scientist. He's actually worked on missions on Titan, on Mars currently. He knows his stuff. So he gave me a hand and he gave me density of wind is 2 times 10 to the minus 8 kilograms per meter cubed. Great number. Don't worry too hard about it. Velocity of wind, 300 meters per second. Super fast. That's a really fast number. And I went with, so then we can just start doing some math. Force of gravity is G. Here's the mass of the moon, 10 to the 22. And then there is my mass, I think. That was a while ago. And then there's the size of the moon squared. And then the answer to that, 9 newtons. The unit of newtons. Don't worry about it. That's just a number we need to know if we're bigger or smaller than, right? Force of wind equals 1/2. I'm not going to write those numbers again, but dW, VW squared, A equals, guesses? 9 newtons, who said 9? Okay, 9, so you think it's equal. So that if I jumped into it, I would hover. Yeah, that'd be cool. Okay, maybe 9 newtons? Any other guesses? Less?
That's like 2 or 3 newtons.
2 or 3 newtons? 2 to 3 newtons. So I'm falling. Is what you're saying. I'm going in. Yeah. Oh, what?
Tiny.
Tiny. Yeah. How do you know it's tiny?
Because I work.
Yeah. Well, there's a number up here that is really telling.
Yeah.
The 10 to the minus 8 really throws it out of whack. It ends up being 0.0006.
You're going for a swim.
You're falling. So what we did here really simply was just what we would call like the back of the envelope calculation. We got a couple numbers, we got a couple equations, and we figured out if something was possible. And even if we weren't bang on with the numbers, the orders of magnitude here are so different. 9 newtons is so much bigger than 0.0006 that it doesn't really matter. It answers my question, right? I know that the answer is, while that wind is launching off there at a really, really high velocity, its density is so small that it's not carrying any oomph with it. So you just plunge down. Even with the low gravity, you're saying like escape velocity or the low gravity, right? Even with the low gravity, I still get pulled down. So that was really interesting. I was super sad that I wouldn't fly off. I thought it would be really cool if it was like an indoor skydiving or something like that. But it was fun nonetheless. John and I wrote an article about it, and it was on the museum website. And then we got to thinking about this, and we said, this is the beginning of the quote from my first slide, no human has ever reclined on the red sand. And we thought, how could we do more of this and actually achieve the goal of trying to transport you, the reader, anyone, to these places and actually participate in something or do something that would bring the experience more towards the human experience, trying to engage some of the senses, like the smell of the moon or the feel of wind on Enceladus. So that was our goal. How could we encourage you to imagine yourselves in these places? We did this in a couple of ways. We started with the moon, and I come back to the moon because this is the only place that we've ever visited as humans, the only place we actually have human senses that have told us things. And we started thinking about it in terms of an unnamed human walking around on the surface of these places. So instead of it just being about the formulae and the numbers and the calculation, we wanted it to actually be a story, something that you participate in. And so this is the first line of the moon chapter. The first thing that hits you is this, in this place, is the darkness. This is a chapter about the far side of the moon, the side of the moon that doesn't face the earth. it gets 2 weeks of daylight, 2 weeks of nighttime, just like any other point on the surface of the moon. So we started really getting into this idea of trying to transport you there through storytelling while trying to live true to some science and getting you to do some activities. And here's another quote from the beginning there. Okay, so now you know what we're going with. We were trying to transport you around the solar system, do some fun science and some math, get a sense for what it looks like when you're there, what it feels like when you're there, and have some fun with it. Answer some weird questions. And so we did that. I have some books here. And then I said, oh, I should go and tell people about all the cool things that I did. And this is really the fun stuff for me. The book is cool, but this is the reason I wrote the book, is because I get to be here and talk with you about cool things in space. And so I reached out when Robin asked if I wanted to do a talk. I said, well, can I ask you all what you want to know about? And here's what you wanted to know. Thank you. There were 30 responses to this poll. Thank you for those that participated in. And it is clear you mostly want to hear about comets, Jupiter and Saturn by far. So Mercury and Venus and an asteroid. Mercury's not even on there. Bennu and Venus, we're not going to talk about today. Unfortunately, it won out to the other three. Let's talk about Saturn. Saturn is in our book a ton. Probably because the same reason why you wanted to hear about it is because Saturn's interesting and it is incredibly varied. It's not just a planet. It's a planet plus a ring system plus an incredibly large number of moons. I've lost count at this point. Does anybody know how many moons Saturn has now? Oh, you do? It's got to be more than that, right? Yeah. 200? Oh my gosh, it changes every day. It's wild. They're finding them all the time. I can't keep track of it anymore. You're looking at Saturn, the really thin ring system, and the moon Titan. So here's a quote from one of our chapters on the Saturn system, specifically about the rings. There is no greater teacher than firsthand experience. Therefore, it's not surprising that Saturn's rings are where the best pilots in the solar system come to learn their craft. What the heck are we talking about? In this chapter, we imagined a story where this is the final test for a pilot in the solar system to learn about orbital mechanics. Because moving in orbit around something is not an intuitive thing. How velocity works, how it affects your orbit, how it changes how far you are from the planet or how close you are. It's really weird how it works. So we imagined a little bit about flying around this place in the plane of the rings and threw a little bit of orbital mechanics in, which I'm actually not going to talk about. What I was more interested in, the reason I wanted this chapter in the book is because when I look at these rings and you imagine like they're all little bits of ice particles just going around Saturn in all these different orbits all the way around. The only thing I can't get my brain to stop thinking about is what would it look like inside the rings? This is where I started with. And I remember sitting down with John, we were chatting. We might even have been in my office. And I was like, John, if we're going to write this book, I need to know what it's like inside the rings. What is it like inside? You see it sometimes in science fiction. Is it true? I have no idea. And here's another quote. As you get closer to the rings, you have a decision to make, over, under, or through. So in our story, our pilot is outside the rings, in the plane of the rings, and approaching the rings through various burnings of the thrusters and deciding, am I going to go over the rings, under the rings, or through the rings? And spoiler alert, the pilot does them all. You do them all as you are the character in the story. But what do we need to know? Let's do this again. What do we need to know about these rings in order to determine what it's like inside these rings? Thoughts? Yes.
Speed at which they're orbiting.
Speed at which they're moving. I like that. Okay. Anything else? Yeah. Density of the rings. How densely packed are the rings?
Size distribution.
Size distribution of the rings. How big are the particles of the rings? Anything else? Thickness of the rings. Oh, very important. Yes. All exactly what I also was thinking. You guys are nailing it. Exactly. Also, maybe what they're made of, that might affect things. One thing I'll say off the bat, I just briefly said it. The rings of Saturn are entirely made of H2O. In fact, as John would say, it's the purest water in the solar system. So if you like somehow scooped up some of that ice particles, you would find very little like debris and dust and rocks and stuff. It's just H2O as far as we can tell, in comparison to other things with lots of ice like Enceladus or Europa. So that's just H2O you're looking at. Frozen particles of ice, all millions and billions and trillions of them going around Saturn in various orbits. But what do we need to know about them in order to determine what it's like in I think Alan, right? Alan? Yeah, you said this one, right? Particle size. How big are these things? How big of the chunks of ice are there? Cassini, the spacecraft that found the plumes of Enceladus, attempted to measure this. And here is the distribution. What you're looking at here, this is, okay, right here. Size of ring or size of particle in meters. So this is something that's 1 meter in size, 10 meters in size, 0.1 meters in size, and so on. This is number of that particle. How many of those that are that size? So do we have a lot of big particles or do we have a lot of little particles? By far, way outweighing. We have, and it says right there, particles less than 1 centimeter in size outnumber ones that larger than a meter, 100,000 to 1. By far, they're little things. They're small. Most of them, the smaller they get, the more of them we have. So that right there tells you that if you were to enter into this ring system, you're not encountering big boulders all the time. You're encountering primarily like snow or maybe hail, I guess, would be the more appropriate analogy. Little chunks of ice, maybe even smaller than hail, really tiny little pellets, I guess. Here's a helpful way of looking at that. We made a plot for our book. So you can see this, you have some the size of telephone poles, a few of them, mostly they're the size of ants or smaller. The next thing we need to figure out is how dense these are packed together. That was another thing that you said. And there's a way to measure this. And you know what's funny? I should have said this at the beginning, is we've never actually been close enough to the rings to actually resolve the individual pieces, even with sending spacecraft to Saturn. Cassini itself, the spacecraft Cassini, actually went and flew between the ring and the planet itself. It actually flew through there a bunch right before the end of the mission. And even that close was not close enough to resolve the particles. So we have to find other ways to try and get a sense of how big these things are and how tightly packed they are. And one of the ways we do this is with this experimental setup you see here, where you have a spacecraft there, Cassini. It's orbiting around Saturn. And every once in a while, if you set the orbit correctly, then the ring system will be between Earth and the spacecraft. So you can get smart and you can beam stuff through the rings and see how much of it makes it to Earth. So you send some radio signals through there. See how much of the radio signals make it to Earth. You can also do this experiment with other things that are naturally in space, like stars. So you can watch Saturn slowly pass by background stars and see how much of the light from the star is dimmed by the rings. This is occultation science. It's the occult. I'm just kidding. So doing this, lots of work was done on this. Here's one of the outcomes that came from it, showing you the particles, the size of particles and how packed tightly they are together. Ones that are in purple lack particles of size less than 5 centimeters. So there's the purpley parts there actually don't have really small ones. They're more spaced out with bigger chunks. So it's a little more nuanced than the average graph that I showed you. The green and the blue are dominated by those smaller particles. And then the white is so saturated, the white parts is so dense that most of the beaming isn't getting through, and it's tough to actually nail down distribution and density. And that's the C ring. Or sorry, the B ring. Here is so you have Saturn over here and moving the edge towards the edge of the ring over here. And on the top, you have something called optical depth. I think that optical depth is a measure of how much light can get through or scattered. There's the numbers of optical depth. And here's how thick the rings are. I think that was how thin are these rings? How tall are they? And what's incredible is these things are no more, this ring system is no more than like 30-ish meters thick. It spans hundreds of thousands of kilometers wide, but it's like 30 meters thin. It's incredibly thin. When you have all this information, when you have like curves of density and like curves of particle distribution, you can get a sense for how much light is going to make it through. And we use something called optical depth. It looks like this. A fun equation. There's the optical depth number. This is the number of how much light you started with. And this is how much light makes it out. Or makes it through. And if you increase this number, then the amount of light you get coming through the rings goes down and down and down and down. And what we found, looking at all the different numbers that came from the different portions of the rings, is that there are places in the rings where the optical depth is where it's so thick that almost no light can get through from one side to the other, even in like a 10-meter space. So the optical depth is so high that you send light in and it just scatters around inside. And nothing really makes it to the other side. So that tells us that if you enter those portions of the ring, you're basically kind of like wading through a fog with like little pellets of ice, some bigger chunks here and there. Other places in the rings, a lot of light makes it through. The optical depth is low. So in that case, you would be encountering the classic one that you're thinking, where there's big chunks, but you can see through it pretty easily. And we had an artist work with us, Michelle Parsons, who gave us one of those ideas of what it would look like. So this is at the end of the story. The pilot has visited a few places in the rings, seen what it looks like, and is now heading home. Passed their test. Okay, that's some fun, right? What'd you think? That was our chapter on the rings of Saturn. Questions on the rings of Saturn? Well, yeah, that's a great question. Yes, so you have the ring system. Everything you're seeing there, all the dense parts and the thin parts, the gaps, the weird like little bit up here, this huge gap right there. That's the entire ring system is shepherded by a bunch of things called shepherd moons, as you're talking about, of varying sizes. There's some really big ones that live inside the rings, some really small ones, and there's some even tiny little ones that create these little like propeller shapes. If you've ever, you should Google Saturn rings propeller shapes. There's some really cool images. So those moons have enough gravity over the eons and eons of orbiting to gradually shape and contour and sort of shepherd and keep the ring particles in certain places. So you're asking if the pilot itself, you being the pilot, flying around in your little spaceship, would you have enough? I think that my intuition, that's a great question. We would have to do the calculation. My intuition would say that you wouldn't have enough to do huge damage to the rings, but you would have enough to do some, like gravity works on mass and on distance, right? And so if you get close enough, any small amount of mass would affect other masses. So I think if you're moving through something, you would affect it. But on the scale of this, like creating a gap or creating ripples or stuff, probably not. But that's just a guess. That's a good question. Yeah. Great question. So in the story, you have to take into account the orbital mechanics. So the pilot is orbiting Saturn, like out here. And then if the pilot wants to go towards the rings, the pilot needs to shrink their orbit by burning their jets in the direction they're going. That'll make them plunge towards. And then you're sort of like entering the rings on an angle. Well, to get out of, like, you would be going through, and that would put you on the other side of Saturn at your closest approach, but then you'd end up back on the outside the rings on the other side. You'd have to do some like random burns to like stay inside. Yeah. It's orbital mechanics is really fun. Yeah.
So Saturn's rings, I've heard, were caused by a collision in the past. And would all the dust and ice kind of like collect everywhere in orbit, spaced out around the planet? So how did it get into a 30-meter ring?
Great question, Benjamin. You have two things that you highlighted there. Okay. The rings of Saturn, the question of how old the rings of Saturn is a really interesting one. And it seems the literature seems to be bouncing around in the argument of whether they're really old or really young. I think the literature, John would correct me if I'm wrong, the literature says that the rings are actually rather young. Even if you go back to like the age of the dinosaurs, the rings may not have been there. We just happen to be lucky because there was some kind of event recently in the last tens of million, maybe 100 million years, a moon, probably like Enceladus, an icy moon, got too close. It could have been a collision between two moons. I think the literature thinks that there was a moon like Enceladus, maybe not as big as Enceladus, got close enough to Saturn that tidal disruptions started tearing it apart. It's called the Roche limit. It's where an object gets too close to another object and tidal forces literally start tearing it apart. But if it's moving, if you can simulate this, and if it's moving fast enough, or at the right angle, you can start tearing it apart and the ice layers on the top can get torn off, but the rocky stuff underneath, if it's a differentiated moon, would end up plunging into Saturn, lost forever. And so you're left with the ices you're left with ices in orbit. So that's how you end up with ices. I haven't gotten to your question, but I'm getting there. Now, the question you have is, okay, well, if it was a collision, or if you do have this catastrophic tearing apart of a moon, how come it's 30 meters like this and not like some big cloud of debris? And the answer to that is, if you give it enough time, spinning things tend to flatten. And it's primarily because if in a system that's spinning, all the things that are already moving in the spinning direction are sort of not going to hit anything much very often. They're kind of safe. But all the things that are like going like this are eventually going to hit things and either become part of the rings or become part of Saturn. So if you give it enough time, the up and down motion kind of cancels out and you end up with like flat stuff. And the stuff that was already spinning like this kind of just stays there forever. And the rings are slowly falling onto Saturn. And eventually, we think the rings would disappear completely, or at least become a shell of their once former glory. But that's how you flatten out. And there's lots of flat stuff in space. There's galaxies are flat. The ring systems are flat. When things spin, like nebula, when a solar system is forming, the nebular thing flattens out into a nebular disk, and that's where the planets form. Spinning stuff. That's what tends to happen. That's a good question. I mean, the short answer is I have no idea. But why do you have dense things in some areas and not dense in some areas? I don't have a great answer for you, but my suspicion would be it's the result of the shepherding. So there's various moons all speckled within there that are like, so the deeper answer would be it's probably related to resonances, where there are some orbits that are safer than others depending on what's nearby. And so moons can like push things into tighter spots. It's the same thing that they're like safe orbits, like the Trojans around that follow Jupiter. But I don't think I have much more than that. It's a good question. I was very happy so just like Enceladus, the emotion I had was disappointment. when I was like, I jump into the plume and I'm going to fly into space. I was disappointed that's not the case. But this, my excitement was that there are places in the rings that you can go that you, even though it's like 10 meters, that's like a little bit taller than this room. Imagine being in this room and you just could not see out of it because it's so dense with ice. Just little speckles of ice floating around. Wild, right? Super cool. I'm not done with Saturn. I'm actually not even going to talk about Saturn. I'm just talking about its moons and stuff. This one, I'll do this one quickly, but this was a really fun one. Has anybody ever heard of a Hyperion before? Some of you who are the moon fanatics and the astronomy fanatics. Hyperion's a moon of Saturn as well. It looks like a piece of like sponge rock or coral. Is, you know, when you look at it, you're like, oh, that's coral, right? It has this really pockmarked surface. Very, very interesting moon in so many different ways. You can see some of the interesting things it has. It's the largest non-spherical moon of Saturn, so it's not big enough to have crushed itself into a sphere. It actually doesn't have I shouldn't say it that way. It doesn't have a consistent spin. So even though it does spin, and there is a way of like measuring like a spin time, it actually is a bit chaotic and it kind of tumbles around randomly a little bit. This is a result of being weirdly shaped and being near a big gravitational source and other gravitational sources like Saturn and Titan, the moons around. So it kind of tumbles around weirdly. But it has this sort of weird claim to fame in the solar system, or at least in the Saturn system. And that is that this moon is highly porous. It has a high porosity. Any geologists in the room would know what the word porosity means. This is a measure of how much empty space there is inside. So, you know, if you crack open rocks, sometimes you'll find like little air bubbles or something, stuff not filled in by rock, just open space inside the rock. This one has a really high amount of that. This entire moon has a really high amount of that. Measuring at 400 kilometers by 200 kilometers by 200 kilometers, it's got a lot of empty space in it. How much? About 40%. That's high, right? 40% porosity. So I take that literally to think 40% empty space. And so when we were writing this, my natural question, I don't have a little astronaut, Jesse. My question was, well, what would it look inside? What would that look like? If 40% of that is empty space, what would it be like inside that? Could I go inside it? So I started playing with some numbers. What could 40% porosity mean? So what's that?
Can be gases inside that.
It could be gases. Totally. Yeah, you don't want it, yeah, it wouldn't be atmosphere like ours, that's for sure. Yeah, who knows what it'd be, right? So I started playing with some numbers. I wanted to know how big of like an empty space chamber there could be. So I wanted to play around with a simple equation. The volume, 4/3 pi r cubed. This is the volume of a sphere. Remember your grade 9, I don't even know what grade that is. Your formula for the volume of a sphere. And I wanted to know if I had a sphere that was 40% empty space, how big would those spaces be? So I started playing around with, what if I had something the size of like a centimeter? How many of them would fit inside a volume of this moon? What if I had a bubble the size of a meter, or a bubble the size of this classroom, or a bubble the size of bigger, or, you know, I started playing with all these numbers. And so first I needed to know how much space I was dealing with, how much volume I was dealing with. And if you put in those numbers here, so if you put in for R, the 400 by 200 by 200, you end up with something like 9, I'm just going to round it. 9, almost 10 billion, 10 million, 10 billion, a lot of cubic space. So that's the whole moon. But we're saying 40% of that is empty. And so I started saying, what if the gaps were 10 meters in size? Say, like, so 10 meters, that's like a gap the size of this room, right? Well, fitting inside of a volume of that, how many would fit in? Use simple division. Trillions. Trillions. So you're in just playing with some simple volume calculation of a moon that's 40% porous. We imagine that if you somehow got under the surface of this moon, you might encounter something this big, this empty. Maybe. What if it was like something like 10 kilometers? Do any of those exist? The answer is you could have thousands of them. So this weird moon of Saturn's being so porous, with all this empty space, we started playing with a random equation, and we realized that it might be a spelunker's paradise. So if anybody here is a fan of cave diving. We wrote this story. I don't know if anybody's ever seen there's a dramatic retelling of the event that happened. I think it was in Thailand, of a boys soccer team that got stuck inside of a cave.
Elon Musk.
Elon Musk?
He sent us some.
What?
He wanted to send us some.
Musk wanted to do it? That guy, yeah. Well, that movie is gripping, and thankfully all the boys made it out. It was crazy. But when we were writing this story, we were sort of picturing going through these like little tunnels. And so you, the reader, are investigating the caves of Hyperion, encountering small ones, encountering big ones, and even encountering some the size of like maybe a city inside this 400-kilometer moon. It was a fun exercise in what porosity could mean. Questions about Hyperion? Okay, we're done with Saturn. On to Jupiter, your second, one of the second? I can't remember which one was first, second, and third on your poll. Okay, what weird questions should we come up with about Jupiter? Do you have any questions about? Yeah. Can you land on Jupiter? Sadly, no. But there is a place, and this is exactly what this chapter is about. If you descend into Jupiter, there is a place where it gets to be Earth pressure. Eventually. That's an interesting question. What would it be like to enter the atmosphere of Jupiter? This one, we're like, we got to be a little more crazy than that. We need to think about what it would be like to skydive in the atmosphere of Jupiter. This is a great way to picture yourself as a human. Has anybody here been skydiving before? Yeah, a couple. Oh, nice. Yeah, nice. Oh, that's good. Yeah, I have done it myself, and it was awesome and terrifying. So here, you get to apply that knowledge of your skydiving on Earth to skydiving on Jupiter. So there's a couple of things we needed to do to get a sense for what it would be like to descend into the atmosphere of Jupiter. The first thing that we was actually a really interesting calculation to do, and that is the horizon on a planet like this. So this is a really great way of looking at it, where you can see there's Earth and there's Jupiter, and there's a vantage point right there. Imagine you're right there, above the same height above the Earth's surfaces as you are above like the cloud tops, the top of the atmosphere of Jupiter. So you're the same height above both, but on Earth, you have a much shorter horizon. That's the length A. And on Jupiter, you have a much longer horizon. That's the length B. This can be a really tricky thing because we're so ingrained with how far away things are on Earth. So when you are like walking around and you see like a building in the distance, you know viscerally how big a building is. You know by experience. You're in a building right now. You know how big this room is by experience. And so when you see a building really far away with the little windows, you don't think it's really tiny, that like little ants go in there. Your brain says, don't worry, I know how big that is. I've been inside one of those before. It's really big. It must be really far away, right? That's your brain doing all these mental quick calculations to help you make sense of the world around you, making back of the envelope calculations. In places like this, or in places that are smaller, it wonks you out a little bit. And the astronauts on the moon had the same experience, where the moon is a smaller place, so the horizon is even closer. And so when you see something on the horizon on the moon, you think it's really far away because our horizon here is farther than the horizon on the moon. And the astronauts got often tricked to thinking things were further or closer, depending on the size of the rock. They had weird experiences with distance, and it would be the same thing exploring the atmosphere of Jupiter, where when you look at how far away something is, your brain can't comprehend and therefore fills in the gaps. You can do this equation actually really easily. If you want to know how far A and B are, it's actually just like some short triangles. So you go to the center of these places. See, there's a triangle there. And imagine that goes all the way to the center of Jupiter. And there, sorry. And there's a triangle there. You got some simple triangles that you can do. It turns into an equation that kind of looks like, I'll just draw it here. There's the surface. Your height above the surface, the distance to the horizon, the radius of the planet, the radius of the planet. And you can actually do a relatively easy calculation to get these numbers. It turns into an equation that looks like this. 2RH plus h squared. On Earth, something like 500 kilometers. But being the same height above Jupiter, it's actually more like 1,500 kilometers. So your horizon is much further away. And this played into how we imagined looking at clouds going into Jupiter. And that brings me to the next one. What are these clouds all about? And there's some really wonky things that happen with the clouds on Jupiter. So here is an altitude temperature map with a sort of pictorial reference of what kind of layers you go through as you enter the atmosphere of Jupiter. So imagine you're sitting up here, little skydiver you, and you're going to start falling into the atmosphere. You start up here with a very, very low density, because the tops of the clouds are just like mixing with space. So you're going from the vacuum of space to a very thin atmosphere. And as you descend, the further in you go, the thicker the atmosphere. Yes?
Is that top layer clear? Like, would you be able to see through it?
Yes, absolutely. You'd be able to see through it. Yep. So you'd be seeing, as you approach, what you actually see is the troposphere below. The troposphere is full of all these clouds of different layers. The first layer is ammonia clouds, and then you have water clouds on the bottom, and you got ammonia sulfide in the middle. So yeah, you would be able to see through it. You would. The interesting thing is that as you get into it, as you descend into it, the size of the particles, even though it's not it's primarily hydrogen and helium in Jupiter, but the size of the particles are sort of similar to the size of atoms in our atmosphere, because atoms are roughly the same size as each other. So you end up getting similar scattering happening, and the further in you go, you start getting sort of tinges of blue. So it actually would have a little bit of a tinge of blue at some places up there. So we were interested in, if you're diving into the atmosphere of Jupiter, how fast would you be moving? And this is getting into a terminal velocity type equation, where as you fall, gravity's accelerating you, but atmosphere is pushing back on you to slow you down. And there's a terminal velocity where you can only fall so fast before the atmosphere slows you down to a constant velocity. So we did some of those equations, calculations at the various levels of the atmosphere of Jupiter. Up here at the top, where the atmosphere has something like, you're sort of transitioning from space into a thin atmosphere. The amount of pressure you get back is very, very low from the atmosphere. You're moving at something like 2,000 kilometers an hour. So you can accelerate to a pretty high velocity in the upper layers. As you get further down, when you get to just to right here at the entrance to the ammonia clouds, you end up slowing all the way down to 90 kilometers an hour. Now, we did imagine, now there's one factor that we haven't included here. We imagined that we had a big parachute that we deployed. Yeah, I know. We deployed a parachute because that it gets really unwieldy and you can like accelerate like crazy. But, and then if you get right to the bottom of the water clouds, you can get down to a slow fall of 20 kilometers an hour. These are as you're descending in, you start experiencing these different clouds, these different layers, and they sort of, some of them act like the H2O clouds sort of act like ours. They look like white clouds. They might even snow or rain, depending on the temperature fluctuations. So you have like interesting weather happening in all three different layers. Here's a painting from the book. So in short order, you slow down to terminal velocity, but with just a pressure suit and a parachute pack, that's something like 2,000 kilometers an hour. But it's more, something's really, so getting back to the question that you had of like, what would it look like? I can't remember what your exact question was. Oh, land. No. Yeah. Okay. Yeah, you could. But sorry. No, you couldn't land. But as you get into these clouds, especially when the first layer of clouds is the ammonia clouds, and as you get into the ammonia layer, what would end up happening is light that's scattering, the bonds that ammonia has aren't the same as the bonds that water has. So H2O molecules bond together in certain ways to make crystal structures and ices. And when we see light going through that and scattering, you can get things like rainbows and weird arcs and stuff. Has anybody ever seen, I'm sure some of you have seen a rainbow before. Has you ever seen like a sundog or like big, huge, like rainbow sundog things? You can get these big arcs going through the sky. They're not quite rainbows. It's more like scattering light, but rainbows are involved. You seen any of those weird atmospheric optical effects before? If you play around with the molecules of ammonia, you actually get cubic type bending of light, and you end up getting weird structures. So this is a painting that was done by the artist in our book. So you get these weird flares of light as a result of the clouds and the snow being a different ice than the clouds and the snow we have here. So you would see these weird optical effects that you're not used to seeing at distances you're confused to understand because the horizon is so far. All this to say, the atmosphere of Jupiter is varied. It's got many different layers. In the story, we have the person plunge into the great red spot because why not? And once you make it out of the clouds on the bottom, and you see the grandeur of the great red spot below you. Wild time. Okay, I have one last thing to talk about. Well, it's over hundreds of kilometers.
Okay,
Yeah.
so it wouldn't hit you like me doing a belly flop into the pool.
No, good question. Good. That's a great question. It shouldn't, no. You're slowly increasing density, so you would slowly decelerate. Yeah. Although I haven't done that calculation, and I wish I knew how to do it right now. How could we do that? We need to do the impulse. So the layers, that's a good question. So like we're talking about like, what's the difference here? Going from, because the density really kicks up where the cloud layers are. So the biggest force of deceleration you would feel would probably be in like this range here, but it's still over like 50 to 100 kilometers. I can't imagine it's going to be something that's like a belly flop.
Except at the top you were doing 2,000, and at the top of the cloud layer you were doing 90. So almost all your speed is going
Over, I imagine. Well, so I'm assuming that's a great, yeah. I mean, you're going really fast, but I think over this period, like that's that's almost 1,000 kilometers of range, and the way impulse works, even just a little bit of range to decelerate over takes the force away. So that's a really good question. I wish I knew how to calculate that on the fly. I'm sure I could pretend to know how to do it and just call John, and John would, as I have always done.
Sorry, one other question. That is, how much of that top layer is clear that we see through before we don't see?
So
how many kilometers is that?
Yeah, well, as far as okay, I don't have the answer. The short answer is I don't know. But I remember talking through this with John, and really the times when you can't see are the times when you're in the clouds, just like our atmosphere. So you would be able to see, like when you look through our atmosphere, eventually there's a distance you can't see anymore when it's like hazy and it's like gets wobbly, right? So I think the same effect would happen. So you're looking at hundreds of kilometers you can see to your horizon, at least. But once you're in the clouds, then it's like you're in clouds like here. Yeah. So you can see pretty far just in the atmosphere if you're not in the clouds. Oh, I don't have the words off the top of my head.
You have to buy the book.
Yeah, you could skim the book here without buying it. Yes. So what I was trying to get at with these calculations is it's described as like bigger than life. So like the Great Red Spot is it's the size of Earth, right? It's bigger than Earth, right? And as you descend into the atmosphere, you're sort of descending into like a walled area. It's almost like, we don't get into the whole structure of the Great Red Spot, but it describes it as being grand and large and like at the horizon. Like you're seeing, you can't see it all in one go. Because, if your horizon is 1,500 kilometers ish and Earth is 6,000 or 12,000 kilometers wide, like you're in a structure that's bigger than you can see. But we describe it as being deeply rooted and connected into Jupiter. And so you sort of feel that grandeur it's described as being very grand. Oh, interesting question. We do that calculation too. Surface gravity. So on Earth, surface gravity is 1g. We can just call it 1g. It depends on if you can do a calculation for like the size of Jupiter. And if you were like, happen to be able to stand at like the cloud tops, how much gravity would be pulling you down. And it's about 2.5 times the gravity of here. So if you could imagine yourself being 2.5 times more massive and walking around, that's what it would feel like. So get like a friend of yours and then half of a friend of yours on your back and like try and walk around. So you'd like, probably most of us wouldn't be able to do that, right? Some strong people with who don't skip leg day can probably handle it. So I guess it wouldn't crush you, but it would be very, very uncomfortable. But that's, how like when you fly in an airplane, so this chapter starts with you're in an airplane in the atmosphere of Jupiter. And in order to fly in the atmosphere, you need to move at thousands of kilometers an hour to generate lift. Anyway, when we're in an airplane on Earth, you can walk around the cabin and you feel 1g, pretty much. Like you're farther from you're 10 kilometers up, but it's still about 1g of gravity. And so if you were on an airplane in the atmosphere of Jupiter, walking around, you would feel 2.5 times. Uncomfortable, but not crushed to death. But the question of like what happens, like if you keep going if you keep going down, so our skydiver pulls out when it's like a little over 1 bar. So the pressure starts getting to like 5 times the pressure of here, almost feeling like you're underwater, but still being able to move. But if you keep going and you keep going down, you can see that the black line, this line here, is the temperature. And it increases the further you go down. The pressure goes up and the temperature goes up. And eventually you get to a point where you would be crushed. Like the pressure would just be so much that you would not be able to survive. And the temperature would be so high, you wouldn't be able to survive. But there's no like solid surface to stand on unless you get to the core. But now we're in a realm of pressure and temperature that doesn't even make sense anyway. Your gases and solids and liquids at that kind of temperatures and pressures don't even act like gases and solids and liquids in the same sense anymore. So there's no real reality that we normally have like that. Fun to think about though. Is there a solid portion of Jupiter in the center? Maybe it's got a hard core, like an iron core metallic ball. I don't think you could stand on it though. So the biggest one that you wanted to hear about was comets, which is cool. I'm not going to talk about 3I Atlas, though that is also a cool topic. So we have a chapter in our book that is all about sun-grazing comets. So there's lots of comets in our solar system. Most of them are beyond Pluto. Most of them have circular orbits going around the sun. And they stay beyond Pluto where it's cold, and comets are primarily made of rock and ice. There's a lot of ice on them, a lot of rock on them. They're made of a variety of different ices, not just H2O, but there's ammonia, carbon dioxide ice, ammonia sulfide ice. Like there's a mixed mash of ices on them. And then even beyond the little region beyond Pluto, there's another region really, really far away. We call it Oort cloud, a big cloud of icy things that orbit around the sun. But every once in a while, we have comets come into the inner solar system, as you know. And when they get close, that ice starts turning into gases and turns into tails, and hopefully very visible to us. And every once in a while, we get to see one, and it's really, really great. Sometimes these comets are in such incredibly elliptical orbits that bring them so close to the sun, we call them sun grazers. And their fate is sometimes they make it out and sometimes they don't. Sometimes they whip around the sun and outgas and fall apart. Sometimes they don't fall apart and just sort of just make it through. It depends on how long they're there, how fast they're moving, what they're made of, how densely packed they are. So we imagined, could a human survive that trip? We have, this is Comet 67P of great fame because it was landed on by the European Space Agency, the mission Rosetta. This is just a wonderful image of what a comet actually looks like. And you can even see it starting to outgas. Here is the first line of our chapter. Now you've done it, you say out loud as in frustration fills your thoughts. Of all things, shipwrecked on a comet. And so we imagine a space miner who is going to comets as a job to mine the ices and minerals, and then their spaceship breaks, and they're stuck on a sun grazer, and there's no one that can make it there to get them. So they need to figure out what to do to survive the trip around the sun. I won't tell you if you survive, because remember, if you, the book is written in the second person, so it's actually you, the reader, who's doing this. So I won't tell you if you survive. But one thing we can talk about is how fast this thing is moving, and talk about orbital speeds a little bit. I think what I have like 2 minutes left. So this is the sun in the center, and that orbit is Pluto. Okay. Does anybody know roughly how fast the Earth is moving in kilometers an hour around the sun? Like how fast we're moving forward? Oh, yes. In kilometers an hour? Yeah, times 1.6. Mathematician. Exactly, about 100,000 kilometers an hour, roughly. 100,000 kilometers an hour, the Earth is moving forward. What about Pluto? I like the way you're thinking. Farther away, slower. Correct, but not that slow. About 10,000. So it's still pretty fast. Earth is moving 100,000 kilometers an hour around the sun. Pluto is moving about 10,000 kilometers an hour around the sun. It's farther away from the source of gravity. Therefore, it does not need to move as quickly to stay in its orbit. Now, comets can be much further away. They can be on orbits that look like this. And hold on. It'll turn it into, yeah. There's our sun grazer. Out here, how fast do you think they're moving? Real slow. Don't worry, I get to cheat. I have a cheat sheet. Maybe 1,000 kilometers an hour. So we're way down now. Earth is moving 100,000. Comets way out at the edge of the solar system are moving like 1,000 or maybe less kilometers an hour. But if they're on this orbit and they're out here, really slow. But if they go this way, they're literally falling down the hill towards the sun. They're literally just imagine like you falling towards the sun. The sun is a source of gravity. You're falling down the gravity well. You're accelerating. You're picking up velocity as you go. So how would we calculate how fast, if we know how fast orbital speeds are out here, how would we calculate how fast it's moving when it whips around the sun at its fastest right there? Kepler's laws, exactly correct. Well, it's a mix of Kepler's laws and energy law and energy conservation of energy, but totally correct. There's an equation that in rockets, a very famous rocket equation. Does anybody know the famous rocket equation? I know at least Robin knows it. I know it's just like ugly. Gm, gravitational constant, m is the mass of the object that's being orbited. R, this is where you are on your orbit, and A is the size of the orbit. So with this equation, it's called the Vies-Viva equation. Vies-Viva equation. It helps you calculate velocities at any point in an orbit. And if you plug in the numbers that we were just playing with, can anybody guess how fast the comet would be moving after it's picked up all of this gravitational momentum, it's turned all its gravitational potential energy into kinetic energy? How fast is it moving when it whips around the sun as a sun grazer? Guesses?
500,000.
500,000. Interesting.
Kilometers per second.
I can't do that math in my head though. What is that in kilometers an hour? I don't know. Yeah. Okay. I know the answer that we put in the book because I have the cheat sheet. 1.5 million kilometers an hour. So we imagine you, the astronaut, has tried to make this trip around the sun. This is Comet Halley looked up close. So this is what a comet looks like when it's starting to really outgas. This is Halley's comet, I think 86, right? Yeah, 86. So here, just to sort of wrap up everything, this astronaut on this comet is in a place that is outgassing so much you can no longer see. The density, all the ices are turning into a fog around you. It's not lifting you up, but it is sublimating around you. You're feeling the shifts of the comet below you as ice disappears, rock crunches down. There's changes, there's like little mini earthquakes. And you end up moving at 1.5 million kilometers an hour, faster than any human has ever traveled, including the Apollo astronauts. Okay. Basically, that's the book, us daydreaming around, coming up with weird things to think about and trying to communicate it to you. And I just want to say I have two conclusions from this. I came up with two things that I did not realize I was searching for. And that was that us as the authors, as the teachers, we asked way better questions about these places by attempting to imagine these weird scenarios. So I was not expecting that. When you learn about a planet, you sort of like open a textbook and you start learning about it. But when you like think, well, this is one from Robin. Like, what if I could I skate? Could I get on my ice skates and go skating around on Enceladus? Like, I don't know. How do you figure that out? And then you like have to learn about ices and structures, and it's a whole thing, right? So we ask so much better questions about the places by this process. And for you, the telling of the story was the attempt of getting the human to be transported to that place. And I think that really spoke in the book. You actually get to experience the place, not just read about the place. So last thing I'll say is just thank you so much for giving me this forum, because when you make something, you don't realize how much you want to talk about it and how proud you are of it. And I don't really get to talk about it a lot. And so I'm really proud of it. And I had a lot of fun doing it with John. And so thank you for taking a little tour through it. Thanks, everybody.